slide to you, showing you how to use the theorem and solve any theorem equation. Okay, we, uh, we will begin with eighth degree from the equation has to be solved using theorem of Ezouidi and prepare also drink your cafe and prepare also some paper sheets and pens, scientific papers, and work with this hard example. Okay, we will just show how it works and how the roots will be derived using my first formula or the theory of me. Okay, let's start, colleagues. This is the example. Okay.
Work for solving a specific problem.
Exactly. Finding the roots of this, well, very complex polynomial equation. So our mission,
We're going to navigate this thing, understand the main challenge,
which is this 8th degree polynomial, right? With
Yeah.
all its complicated bits.
Yeah, and follow the method the document lays out to get to the answer. It looks intimidating, I admit.
Definitely does. But I think there are some really cool insights hidden in there if we trace the steps.
Absolutely. So the document zeroes in on this one polynomial, px. And like you said, it's 8th degree.
Yeah.
Highest power of x is 8. The source gives its form as px dx LKLS plus AKLSA plus falsa AKLS plus FLXI lurs plus LS.
Okay, just seeing all those L's and Q's, it feels pretty heavy already. And those coefficients, the LRQ things, they aren't simple numbers, are they?
No, not at all. The document lists them right away. They're these specific numerical values, often fractions.
Like what?
Well, L euro is 16. That's simple enough. But then L Q equals 732 divided by 8 squared.
Okay.
L was 225920 over 8 cubed. L shu is 4449726 over 8 to the 4th. It keeps going like that.
Wow.
L is 5579968 over 8 euro. L euro is 435050468 over 8 euro. L is 192822824 over 8 euro. And finally, L euro Q equals 37196577865 over 8 euro.
Good grief. So finding the roots means finding the x values that make that whole monster equal 0.
That's the challenge.
So where do you even start with something like that? I mean, solving 8th degree polynomials isn't exactly straightforward.
Right. And that's where the document's specific method comes in. It doesn't just, throw the quadratic formula equivalent at it because there isn't one for degree 8.
Uh-huh.
Instead, it starts by calculating a new set of values. They're called ZRQ first, and then later L euro.
Okay, SRQ and SRER.
And these are derived directly from those complicated LRQ coefficients we just saw. The document gives specific summation formulas for how to get them.
So step 1 is kind of transforming my input, changing those coefficients into something else. Why? What do these values represent?
It's a common technique in algebra, actually. Calculating these sums, these theta values, can sometimes reveal hidden symmetries or structures in the polynomial.
Oh.
They relate to sums of powers of the roots. Manipulating them can sometimes simplify the problem dramatically. The source shows the formulas and then gives the results.
What results did it get for these values?
It lists SQ14, SQ equals 36, SQ H98, SQ equal 276, SQ equals 794.
Yeah.
It also mentions calculating SQ and even FQ, though that one uses a different looking formula.
Interesting. And while it's doing these calculations, there's something else mentioned repeatedly, a specific tool or formula.
Yes, exactly. It keeps referring to using the discriminant formula of Mourad, Sultan, Ezouidi, H-ism.
Mourad, Sultan, Ezouidi, H-ism. That sounds quite specific.
It does. The PDF doesn't actually show us the formula itself, which is a bit of a black box for us, but its application seems absolutely crucial for the steps shown.
Like it's the engine driving the process.
Sort of, yeah. It seems to be used at several stages, indicated by K0 through K8 in the doc. It's clearly key to moving between coefficient sets or making simplifications.
And near those mentions, I noticed rows of numbers like 1, 4, 6, 4, 1, and 08, 28, 56, 70, 56, 28, 8, 1. Those look familiar.
They should. Those are binomial coefficients, straight out of Pascal's triangle, right? The rows for powers 4 and 8.
Yeah. So their appearance there next to the specific formula mention, what does that suggest?
It strongly hints that this Mourad, Sultan, Ezouidi, H-ism formula, or the process using it, probably involves things like polynomial expansions or manipulations where these coefficients naturally appear, maybe related to symmetric polynomials or something similar.
Okay, so we start complex, we derive these A's values, we apply the special formula. What's the payoff? What big discovery comes out of all this computation?
This is where it gets really interesting. And it's a critical finding the document highlights. After all these steps, it turns out that some of those derived coefficients, specifically the SRR values, are actually zero.
Zero? Really? Which ones?
The document explicitly states SRR equals 0, SR equals 0, and SR equals 0.
Wow. Half of them, the even indexed ones. That sounds important. What about the odd ones then?
Those are non-zero. It gives SR equals a 936, SR equals 446, SRO equals 2196, and SR equals 319065.
Okay, so we have these specific zero and non-zero values. What does that finding do to the original polynomial we started with, the big messy one?
This is the elegance of the method. The whole point of calculating these SRI values using that specific formula was seemingly to transform the polynomial into a form where these values act as the coefficients. The document implies the polynomial px can be rewritten using them.
How so?
It shows a form like px, x to the Harrison, x Harris, plus x, 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 please, x equals x. Notice the alternating signs.
And since pseudo, and set are all zero.
Exactly. Poof. All the terms with all powers of x, and the x term, they just vanish. Because their coefficients are zero.
Okay, that is a dramatic simplification. So what's left?
The polynomial becomes x plus x plus x plus x plus s plus s equals 0. And plugging in the non-zero values, we found x plus 446x plus 465, 0.
That's much cleaner. We went from that beast with fractions over powers of 8 and every term present down to just even powers and, well, relatively nice integer coefficients.
Relatively nice, yeah. Still an 8th degree polynomial, but a very special type.
So how do you solve this one? It's still 8th degree.
Now, the document uses a standard trick, a really neat substitution that works precisely because only even powers are left.
What's the trick?
It sets xx source 6 is xx, a new variable, capital X.
Okay. So if x squared is x, then x to the fourth is x squared.
Right, and xx is xx and xx.
I see. So the whole equation transforms.
Perfectly. The 8th degree equation in x becomes a 4th degree equation, a quartic in x. It becomes x row 36x row plus 446x row 6, 2196 plus 3465 equals 0.
And look at the coefficients. Negative 36, 446, negative 2196, 3465. Those are exactly the non-zero values we had before.
Precisely. 0, 0, and hex row.
Okay, now a 4th degree polynomial. That's much more manageable than an 8th degree. Did the document find the roots for this x equation?
It did. And this is maybe the most surprising part of the whole thing, given where we started.
What are they?
The roots for x are just 3, 7, 11, and 15.
After starting with those wild fractions involving huge numbers and powers of 8,
yeah.
That feels like magic. How?
Well, it's not magic. It's the power of the mathematical technique they used, right?
Ew.
It stripped away all the surface complexity and revealed this incredibly simple underlying structure in terms of x.
Okay. So if those are the roots for x, how do we get back to the roots for our original polynomial, px?
It's the final step. Remember the substitution. X.
Right. So x must be the square root of x.
Exactly.
Right.
X.
So for each of those x roots, 3, 7, 11, 15, we get 2 x roots.
That's it. The roots of the original 8th degree polynomial, px, are 3 GAN 7, 11, and 15.
Plus or minus for each. That gives 4 pairs, so 8 roots in total, which is exactly what we'd expect for an 8th degree polynomial.
Precisely. So the document successfully found all 8 roots.
That's quite a journey.
The source also shows these roots in a slightly different format later on. It connects them back to that initial coefficient, OQ.
The one that was 16.
Yeah. It writes the roots as LQ$8, where S key are those roots we found for x, 3, 7, 11, 15.
Okay, let me see. So using LQ16, that gives 16 null 3, 8, then 16 then ends to 7, 8, and 16 null 15, 8.
It's just another way to express the same 8 solutions we found from MCAS.
Interesting. It ties it back to the beginning slightly.
And one more thing the document includes, sort of separately at the end, it does a quick calculation using a different set of numbers. Yeah, the set 24, 8 negative 8, negative 24. It calculates SER and S02 for this set, finding S0 is 0 again, and S0 is 1280.
Any idea why that's there?
It's not directly solving our main polynomial. It seems maybe like an appendix or an example, perhaps illustrating how the S0 calculation works on a simpler symmetric set of numbers. It shows the method isn't only for that one big polynomial.
Okay, got it. So let's recap the main path then. We started with this frankly, terrifying 8th degree polynomial, really complex coefficients.
It's defined by those specific LRQ fractions, yeah.
We watched the document use a specific method, calculating these intermediate Ezouidi values.
And applying that key tool, the Mourad, Sultan, Ezouidi, SEOSIM discriminant formula, whatever that is exactly.
Which led to this critical moment where certain derived coefficients, the SURR with even indices, turned out to be 0.
Right, a major breakthrough. That zero coefficient finding just blew open the simplification.
It let the polynomial collapse into a much simpler form, one with only even powers of x.
Which then allowed for that clever XEOPOE 2x substitution.
Turning the 8th degree problem into a manageable 4th degree one in x.
And that x equation, against all odds it felt like, had these beautifully simple integer roots. 3, 7, 11, and 15.
And taking the square roots of those gave us the final 8 roots for the original beast. 3, 7, 11, 15.
Yeah, so this deep dive really showed how a very structured, specific mathematical approach, even if it involves complex steps and perhaps non-obvious formulas.
It's like that discriminant formula.
Exactly. How it can cut through what looks like impossible complexity to find a hidden, simpler structure underneath. It really highlights the power of transforming the problem, changing coefficients, substituting variables.
It's a fantastic example of finding simplicity hidden inside complexity.
It really is.
So here's something to chew on, maybe. Think about where we started those incredibly complex fractions, the LRQ coefficients, with huge numerators and denominators involving powers of 8. Just seemed arbitrary almost.
Very specific.
And yet, the whole elaborate process documented here, it boils down to revealing these 4 simple integers, 3, 7, 11, 15, as the absolute core of the solution for the transformed equation.
Yeah, it's quite contrast.
So what does that tell you, or what might it imply about the deep structure connecting those complicated initial coefficients to these fundamental integers? Is there some hidden pattern or relationship in those LRQ values that demands the solution involves 3, 7, 11, and 15? What other really tough math puzzles out there might just be waiting for us to find the right transformation, the right derived values to reveal a similar kind of hidden, simple numerical relationship at their heart?
Thank you for listening. This is an example of 8th degree common equation, and we explained how the theorem works and how the approach method of most really derive all the 8th degree, all the 8th symbolic exact roots, okay, which are equal to 16 plus e to the 3 divided by 8. These roots, and 16 plus a negative root of 7 divided by 8. This is now that we have 4 roots, and these are the other 4 separate roots, okay. Thank you for listening, and see you in the next time. Okay, goodbye.